This is part 1 of lecture 5.2, finite sets. In this video, we will state and prove some basic properties of finite sets, including facts about subsets of finite sets. Recall from the end of the previous lesson that a set S is finite if it is either the empty set or numerically equivalent to the set of integers from 1 to n for some positive integer n. In the second case, that is, in the case where the set S is numerically equivalent to the set of positive integers from 1 to n, the process of defining a bijection from S to the set of integers from 1 to n is called counting. If S is numerically equivalent to the set of integers from 1 to n, then the number of elements of S is n. If S is the empty set, then the number of elements of S is 0. This gives us an alternative definition of the cardinality of a finite set. If S is finite, then the cardinality of S is simply the number of elements of S. Thus, if S is empty, then the cardinality of S is 0. And if S is non-empty, then S is numerically equivalent to the set of integers from 1 to n for some positive integer n, and the cardinality of S is n. Also, two finite sets are numerically equivalent if and only if they have the same number of elements. We now prove some results about finite sets. Please note that although these results are very elementary and obvious, our goal is to learn how definitions and earlier results are used to construct rigorous, detailed proofs of these statements. The first result that we shall prove is the following. If S is a finite set and X is not an element of S, then the union of S and the singleton with element X is finite, with cardinality equal to the cardinality of S plus 1. We begin the proof by assuming that the set S is finite and the object X is not an element of S. Let n be the cardinality of S, so note that n must be a non-negative integer. Observe that the map which sends X to n plus 1 is a bijection from the singleton with element X to the singleton with element n plus 1. Thus, by the definition of numerical equivalence, the singleton with element X is numerically equivalent to the singleton with element n plus 1. Note also that since X is not an element of S, the set S and the singleton whose element is X are disjoint sets. We have two cases. First, assume that S is the null set. Then the cardinality n of S is 0. So the union of S and the singleton with element X is equal to the null set union the singleton with element X, which, by an earlier result, is equal to the singleton with element X, which, as we observed above, is numerically equivalent to the singleton with element the integer n plus 1. Since n is equal to 0, the integer n plus 1 is 0 plus 1, which is equal to 1. Therefore, the set S union the singleton with element X is numerically equivalent to the singleton whose element is the integer 1. Since a singleton set is finite because it has one element, this proves that S union the singleton with element X is finite. Moreover, the cardinality of S union the singleton with element X is equal to 1, which is equal to 0 plus 1, which is equal to the cardinality of S plus 1. This proves the result for case 1. To prove case 2, we shall use the following result from lecture 5.1. Given sets A, B, C, and D, if A is numerically equivalent to C, and B is numerically equivalent to D, and A and C are disjoint, and B and C are disjoint, then A union B is numerically equivalent to C union D. Assume now that S is non-empty. Then the cardinality n of S is greater than or equal to 1, and S is numerically equivalent to the set of integers from 1 to n. Clearly, the integer n plus 1 is not an element of the set of integers from 1 to n. So the set of integers from 1 to n is disjoint from the singleton whose element is the integer n plus 1. Hence, applying the result mentioned above using the sets A equal S, B equal to the singleton with element x, C equal to the set of integers from 1 to n, and D equal to the singleton with element the integer n plus 1, we conclude that S union the singleton with element x is numerically equivalent to the union of the set of integers from 1 to n and the singleton with element the integer n plus 1, which is equal to the set of integers from 1 to n. Since n plus 1 is also a positive integer, it follows from the definition of finite sets that S union the singleton with element x is also finite, with cardinality equal to n plus 1, which is equal to the cardinality of S plus 1. This proves the result for case 2, which also completes the proof of the claim. Second example, for any positive integer n, any subset of the set of integers from 1 to n is finite. We shall prove this by induction on n. For the basis step, suppose that n equals 1. Let S be a subset of the singleton whose element is 1. There are only two possible subsets S, the null set or the singleton set itself. In both cases, S is finite. Therefore, the result holds for n equals 1, which concludes the basis step. Now we go to the inductive step. Suppose that k is a positive integer and that n is equal to k. For the induction hypothesis, we assume that the result holds for n equals k. That is, assume that any subset of the set of integers from 1 to k is finite. We need to show that the result holds for n equals k plus 1. That is, we need to show that any subset of the set of integers from 1 to k plus 1 is finite. Indeed, let S be a subset of the set of integers from 1 to k plus 1. Then, either k plus 1 is an element of S, or k plus 1 is not an element of S. We consider each of these cases separately. Assume first that the integer k plus 1 is not an element of S. Then S must be a subset of the set of integers from 1 to k plus 1, minus the singleton whose element is the integer k plus 1. In other words, S is a subset of the set of integers from 1 to k. It follows from the induction hypothesis that S is finite. Now assume that the integer k plus 1 is an element of S. Let T be the set S minus the singleton whose element is the integer k plus 1. Then the integer k plus 1 is not an element of T, so T is a subset of the set of integers from 1 to k. By the induction hypothesis, T is a finite set. We now apply example 1. By replacing the set S in example 1 with the set T, and the object X in example 1 with the integer k plus 1, we conclude that T union the singleton with element k plus 1 is a finite set. Note that S is equal to T union the singleton with element k plus 1. Hence S is also finite. This completes the inductive step. Therefore, by the principle of mathematical induction, any subset of the set of integers from 1 to n is finite. We shall use the result of example 2 in the proof of the next theorem. Given two sets A and B, then the following are true. First, if A is finite and B is numerically equivalent to A, then B is finite. Second, if A is finite and B is numerically equivalent to A, then B is finite. In other words, the first statement says that any set which is numerically equivalent to a finite set is also finite. The second statement says that any subset of a finite set is finite. To prove the first statement, assume that A is a finite set and that B is numerically equivalent to A. There are two possibilities for A, namely, either A is empty or A is non-empty. We consider each case separately. For case 1, assume that A is empty. Since B is numerically equivalent to A, B is numerically equivalent to the null set. Recall that by an earlier result, the only set which is numerically equivalent to the null set is the null set itself. Therefore, B must be empty. Hence, B is a finite set. For case 2, assume that A is non-empty. Then, for some positive integer n, the set A is numerically equivalent to the set of integers from 1 to n. It follows from the transitivity of numerical equivalence that B is also numerically equivalent to the set of integers from 1 to n. Therefore, B is also finite. This completes the proof of statement 1. To prove statement 2, assume that A is finite and that B is a subset of A. Either B is empty or B is non-empty. We shall consider each case separately. For case 1, suppose that B is empty. Then B is finite and we have nothing more to prove. For case 2, suppose that B is non-empty. Then, by a previous result, the set A is also non-empty. So A is numerically equivalent to the set of integers from 1 to n for some positive integer n. Hence, by the definition of numerical equivalence, there is a bijection f from the set A to the set of integers from 1 to n. It can be shown that the restriction of f to the domain B is a bijection from B to the image f of B. The proof of this claim is left as an exercise. Thus, by the definition of numerical equivalence, B is numerically equivalent to its image f of B. Now, the set B is a subset of the set of integers from 1 to n. So, by example 2, the set f of B is finite. Thus, B is numerically equivalent to a finite set, and by statement 1, this implies that B itself is finite. This completes the proof of statement 2 of the theorem. You have come to the end of lecture 5.2, part 1. You may proceed to part 2. Thank you for your attention.